Here are the notes for Unit 7.1, Springs. First, we're going to begin with the definition of work. In the scientific sense, work is force times distance. And the force and the distance need to be parallel to each other, or at least some component of force and distance need to be parallel to each other. Now, when we think about the units for force and distance, force is measured in newtons, and distance is measured in meters. So work is measured in Newton meters, newtons times meters. And there's another name for that, and it's the joule, named after a scientist named James Prescott Joule, who lived quite a while ago. So what we were looking at in our opening lab was what happens when we take a spring and we put a force on that spring. So one way to do that would be to hang a mass from the spring and let it go, and the spring would extend. And the force, the hanging force, would be Fg. And then the spring would exert an upward force, a tension force, which we could also call a spring force. And what we saw was that this relationship between how far the spring stretches, so we'll call that delta x, the relationship between how far the spring stretches and the force is a linear one. So again, the relationship between delta x and the force, the spring force, is linear. So I'll make a sketch of that. On the y-axis, I'll put the spring force, and that's measured in newtons. And then on the x-axis, I'll put the position of the spring. So in this situation, if I had a vertical spring, I would create a number line, and I would use that number line to determine my delta x. And what we see is that, again, this creates, there's a linear relationship between force and stretch for a spring. Okay, and I'll refer you back to the lab for more context on that. But basically, the slope, which is rise over run, is going to be the force over, well, actually, it would change in force over change in position. And that's going to be a value k, which we're going to call the spring constant. In fact, I can take this slope equation and rearrange it. If I multiply both sides by delta x, then I get that the force is equal to k times change in x. Or delta f equals k times delta x. If the spring starts from 0, then I'm just going to write Hooke's law as F equals kx. In other words, the force on the spring is going to equal k, which is our spring constant, times the distance it's stretched. And this, again, is named, this formula here, F equals kx, is called Hooke's law, and it's named after Robert Hooke, who was a contemporary of Isaac Newton. They actually had kind of a feud. There's an excellent episode of Cosmos that talks about that. Okay, let's talk a little bit about some more stuff here. So we have got the, let's talk about the y-intercept. In this example, the y-intercept is 0. And that means that if I apply no force, I get no stretch. There are springs that don't start stretching until you put a minimum amount of force on them. So there are springs that have a y-intercept that is non-zero, but in this class we're not going to talk about those springs. If you go on and study more physics and engineering, you certainly can learn more about those. Okay, and now let's think a little bit about what the area would mean. So whenever I look at a graph in physics, I think about two different things. Always, always, always. I think about what does the slope represent? And slope is rise over run. And I look at those variables and I think about what that slope actually means. I'm going to do the same thing with the area. I'm going to look at the variables. I'm going to start with the definition of area, and then I'm going to look at what the variables would represent. So here's what I mean by that. Area is length times width, if I had a rectangle. Here I don't have a rectangle. If I were to find the area under this line, it would be a triangle. So it'd be 1/2 base times height, where my base is x and my height is force. And if I multiply those two quantities together, what happens is I get work. Because remember, work is force times distance, and this is just the force that I exert on the spring times the distance that I stretch it. Now, you may be wondering, well, what about this 1/2? What's going on there? In this situation, because the spring is stretching, the force I'm exerting on it is changing. This 1/2 F is actually the average force. Let's see. So I'm going to take this idea down here to where it says derivation of energy stored in a spring. So I'm going to take this idea and copy it. I'm going to paste it down here. Okay, so this is where I was. So let's apply a little bit more here. So this equation for this line, so usually when we write the equation of a line, we write y equals mx plus b. And here's my y-axis, and here's my x-axis. But in physics, unlike in math, we're not going to use the generic terms for y and x. We're going to use the variables that are on those axes. So what's on the y-axis, oopsie, oh no. So what's on the y-axis is force. Oh my goodness, I'm really making a mess here. There we go. Okay, so instead, oopsie, I did it again. Okay, here we go. Instead of writing y, I'm going to write force because force is on the y-axis. I'm going to write force equals. Okay, next, instead of writing m is my slope, which I have down below. That's k. So now I'm going to write k for the slope. And then instead of writing x, well, actually we kind of lucked out here because the x-axis has x, the position on it. So that's actually happens to be the same variable, okay? So I've got f equals kx is the equation of my line. And of course, b is 0, so I'm just going to ignore that part. Or I'm not ignoring it, it's 0. So it doesn't do anything when I add 0. Okay, so this point right here, how do we get to this point right here from the origin? To get to this point, I would go over x, and I would go up the force. But the force equals kx. So if I were going to name the coordinate of this point, I could call it x, kx. And I'm going to bring that concept, down below. Again, x is the base of my triangle and kx is the height. So if I plug in x and kx for my base and my height of my triangle, I end up with 1/2 times k times x, or 1/2 kx squared. So, as an example, if I had a spring with a constant of 10 newtons per meter, first of all, I could make a graph of that. Let's say that this is 0.1 meters, 0.2 meters, 0.3 meters, 0.4 meters. I could figure out that to go 0.4 meters, it would take 4 newtons of force. And the way that I would figure that out is I would take the spring constant K times the distance stretched, which is 4. I'm kind of painted myself into a corner here. I'll use Notability to help me out. Okay, so on the, let me move this even just a little bit more. So on the y-axis, I know that this needs to go up to 4 newtons. 3, 2, 1. So I've got force in newtons, and I've got stretch in meters. And the graph for the stretching of a spring is going to look like that. Let's say I wanted to find the energy stored stretching that spring. The energy stored would be the same thing as the work done on the spring, which is the same thing as this area. And I could figure it out. I could figure out the elastic energy by doing 1/2 kx squared. So that would be 1/2 times 10 times 0.4 squared. And I'll get out my trusty calculator. Let's see, this is 1/2, maybe I don't need it, times 10 times 0.16. So that's 1.6, I think it's 0.8. So that area is 0.8 joules. And that area is the energy stored when I stretch the spring, and it's also the work that I did to stretch the spring. And one of the big ideas in this unit is that energy stored, energy is equivalent to work done. Again, work is force times distance. Okay, so let's take a look at an example here. Suppose a spring has a constant of 50 newtons per meter. Write Hooke's law for the spring. So Hooke's law is F equals Kx. And this value, 50 newtons per meter, is my K value. So to write Hooke's law, all I have to do is plug in that K value. F equals 50x. If you want to be really fancy, you could plug in the units as well. Okay, part B. How much more energy is stored when the spring is stretched from 0.3 to 0.5 meters? Okay, well, I'm going to make a sketch of this. So 0.1, 0.2, 0.3, 0.4, 0.5 meters, x in meters. On the y-axis is going to be my force. Now, my maximum that I need for my sketch, my maximum x value is 0.5. So if I plug that into my equation, I get that the maximum force that I need is 250 newtons. And then I'll space it out in equal intervals. So the graph of this would look like this. And again, this point right here, my maximum point, has an x value of 0.5 and a y value of 250. Okay, to figure out how much energy is stored between 0.3, to stretch between 0.3 and 0.5 meters, I'm going to find that area. Now this is a little trickier than the last example I did because how much more energy is stored? It took some energy to stretch the spring from 0 to 0.3. To find the answer to this question, I'm going to have to find the area of this shape. Oops. So I want you to think for a second about what is this shape? Think back to your geometry class. What shape is that? It's got two parallel sides, which we would call bases. Now, usually the bases are horizontal. Here they're vertical. And then the height is horizontal. And so this is a trapezoid. And just a reminder that a trapezoid is a figure that has one pair of parallel sides. It's got two bases separated by a height. And the area of the trapezoid is 1/2 b1 plus b2 times the height. In fact, 1/2 b1 plus b2 is the average of the bases. Okay, so to find this area, we're going to do 1/2 b1 for this figure is 150. b2 is 250. And h, from 0.3 to 0.5, h is 0.2. So I'm going to do 1/2 times 400 times 0.2. So that's going to be 40 joules. Okay, let's try another one. Example 2, how much energy does the spring store when it's stretched from 2 meters to 6 meters? So this is the same as the last example. In order to find the energy stored, I'm going to find the area. Here the picture is provided for me. So I'm going to need to figure out B1, which I can get off of the graph. This is 0, that'd be 2, that'd be 4, so B1 must be 4. B2, that's a little harder to see. It looks like 16, 17, 18, 19. And then the height or distance between the bases is 4. So the area is going to be 1/2 B1 plus B2, the average of the bases times the height. So that's 1/2 4 newtons plus 19 newtons times 4 meters. Again, notice what we're really doing here is that this chunk of the equation is the average force. And then the 4 meters is the distance. Okay, so 4 plus 19 is 23. So 1/2 times 23 times 4. So that is 46. And then again, the unit is the joule. Okay, hope that made